All right, so let's get started. So I'm Jinghao. Today I'm going to show you how we can design a safe and usable kernel extension mechanism. So this is a joint work between UIUC, IBM Research, and Virginia Tech. Oops, it's not working. So in recent years, safe kernel extension, exemplified by eBPF, has become particularly popular and have seen a lot of use cases. So those ranges from the networking use cases such as Cilium and Craun to the tracing use cases represented by the BPF compiler collection and BPF trace. And people are actually exploring new use cases of eBPF. There have been research works on applying BPF to consensus protocols and storage systems, as well as custom CPU scheduling and memory management policies. So compared to other mechanisms of extending kernel functionality, and core to eBPF's value proposition is an unprecedented promise of safety. So in the mode of BPF, the developers will write their code in the high-level language and then compile into BPF bytecode, usually through LLVM. And this bytecode can then be loaded to the kernel via the BPF syscall. And at this point, the in-kernel BPF verifier will perform a symbolic execution across all pathable code paths and verify a set of safety properties. So if the program is ever accepted a passive verifier will be accepted in the kernel and can talk to a set of helper functions acting as kernel APIs. So the verifier verifies several important safety properties. Those include the memory and tab safety, safe resource management, runtime safety concerning the program termination and stack usage, and the absence of undefined behaviors. So, but if the verification fails, and this program will be rejected. And then in many cases, we actually don't know why it is rejected. The program looks totally fine to us. And I'm going to tell you that a lot of times, the programs are indeed fine. So you can see that we got this usability problem here. And this is exactly the problem we want to solve. So here is an outline of the talk. So I will first dive into this usability problem, which we call the language-verifier gap in the safe kernel extensions. And then I will present our solution, which is the REX extension framework for closing the language-verifier gap. And finally, I will move on to the usability and performance evaluation. So let's first move into the problem. So here is an example BPF program from Cilium, which is a popular BPF networking project. And here, the code here is pretty simple. It just looks up a service from a BPF map using a key. And if this first lookup does not yield us anything, it's going to redo a wildcard lookup. But this simple code does not pass the BPF verifier. So what you got from the verifier is like this verifier log. It's really hard to understand because it's all in BPF bytecode instructions. It's challenging to map them back even to the source code statements. And the actual error message is also quite confusing. It says invalid BPF context, access equals 44, offset equals 44, size equals 2. But why is it invalid access? So it turns out that in this particular case, the verifier just does not understand the compiler. So here, the program uses the BPF H2NS to convert the inderness of the source port field of the context. And source port is defined as 32-bit int, while the BPF H2NS only operates on the upper 16 bits. So when the compiler sees it, it will just optimize the code to only load the upper 16 bits, which is reasonable. But for the verifier, it checks this context field access based on its size. So it's expecting a 32-bit load, but it only sees a 16-bit load. And as a result, it will just reject this program because of the size mismatch error. So developers actually, in this case, had to put extra effort to fix the problem, and here by using the validor keyword to force a 32-bit load from the compiler. So we argue that there exists a gap. So on one side of your gap is the high-level source language, whose contract binds the compiler and the programmer together and allows the compiler to employ optimizations that are reasonable under that contract. And on the other side is your BPF verifier, which performs the checks based on a different contract at bytecode level. So we call this gap the language-verifier gap. All right, We have already seen one such example where the gap caused issues. And the truth is that this language verifier gap has caused many issues. So based on our study on popular and large BPF projects such as Cilium, IRS, and Craun, we found that developers actually frequently have to implement workarounds to fix the verification issues. So for example, they may need to refactor their code into smaller ones to stay within the verifier's complexity limit. They may need to hint the compilers to generate verifier-friendly code, which is just the case we saw. They may need to tweak their own code to assist verification, dealing with verifier bugs, and even in some cases, reinvent the wheels. So a natural question, of course, is like how we can close this language verifier gap. Well, if we can run the extensions without the verifier, this gap will certainly be gone. But that brings us to another important question, which is like, how can we ensure safety? So our insight is that we can leverage the language part that already exists. And in other words, we can use language-based safety together with the lightweight runtime mechanism. And for example, we can use Rust as our safe language, where we require the extension programs to be written in safe Rust only. And then for the safety properties that are hard to be captured by the compiler, such as program termination, stack usage, we can implement checks for these at runtime. All right, so now let's move to our solution to the problem, which is the Rust Rex extension framework. So here we present the Rex project, which is a safe and useful Rust kernel extensions. And in the mode of Rex, the program will be implemented in safe Rust only. It will then be compiled by our trusted Rust compiler and linked with the Rex kernel crate. So this program can then be loaded to the kernel. And at this point, the kernel will perform some load-time fix-ups to resolve the referenced kernel symbols. And after that step, the program is just like other regular BPF programs. You can just attach it to existing hook points and talk to the same set of helper functions. And during program execution, the in-kernel Rex runtime provides support for exception handling as well as program termination. So the safety of Rex includes the compile time safety from the safety abstraction of the kernel crate, as well as the runtime safety provided by the Rex runtime. So due to the time limit, in this talk, I will focus on the extended tab safety as well as the safe exception handling. So let's first take a look at extended tab safety. So in certain cases of kernel extension programmings, there is actually a desire to safely transform a byte stream into tab data. And it is common, really common in networking use cases, but it inevitably requires unsafe code under the Rust tab system. So let's consider the following example. So let's say we have a payload, which is a byte stream, and we want to extract the protocol field of the IP header from this payload. If it's C or eBPF, as shown in the screen, we can just do the pointer cast, and that's it. But if we're using safe Rust, we will need to first downgrade that payload, which is now a safe Rust slice, into a raw pointer, perform the tab cast at raw pointer level, and finally do an unsafe dereference on that raw pointer. And you can see that this really undermines the safety. So you probably want to ask, OK, why is it safe for BPF, though? So it turns out for BPF, it considers this cast to be safe under two rules. The first rule is that the casting does not create a pointer by casting a scalar value, which prevents us from creating a wild pointer. And second rule is that this new value will need to fit within the memory boundary. So in Rex, we just follow the same rules as BPF and extend the Rust tab safety. So how can we avoid creating pointers from scalars during casting? Our idea is that the compiler already has the full knowledge of all the tabs. So in Rex, we create a new auto trait in the Rex kernel crate. And to those who are not familiar with Rust, a trait in Rust is just like an interface in Java that you can implement on other types. And in the case of our auto trait, it is by default implemented by the compiler on all the tabs where their fields has already implemented this auto trait. So, and in Rust, auto traits can also be explicitly disabled on certain tabs via the negative implementation. And here we add the negative implementation on the reference and pointer types. So after all of this work, we effectively only implement the trait on the tabs where that does not transitively contain pointers or references. So let's take a look again at an example. Suppose we have this struct myHeader, and myHeader contains a non-null U64, which internally contains a U64 pointer. Sorry. So because of the presence of this pointer, non-null U64 will not have an implementation of rex no-ref, and consequently, myHeader will not have an implementation of rex no-ref as well. So to use this to enforce the first rule, we require the target tab of our casting to always implement rex no-ref. And in this way, we just prevent you from casting into any tab that may transitively contain pointers. And to enforce the second rule, we add runtime assertions that performs memory bounds checks to ensure that the target object always fits in the memory boundary. So now let's move on to the safe exception handling from the rex runtime. So it turns out that certain safety properties of Rust itself are already checked at runtime. And violations such as an array out-of-bounds access will just trigger Rust panics. And in user space, Rust performs the Tianyin ABI exception handling upon a panic, where it will just unwind each stack frame and execute the cleanup code. But this is actually not suitable in the context of safe kernel extensions, because stack unwinding in the kernel cannot fail. Otherwise, we may risk causing kernel crashes or resource leaks. And at the same time, just arbitrarily executing user-defined destructors is not safe either. This is because we cannot make sure that those destructors, they do not trigger a secondary panic. So in Rex, we implement our own safe exception handling mechanism in two components, grace for exit and resource cleanup. So let's first take a look at grace for exit. So here shown on the screen is the in-kernel dispatcher function of Rex, which is responsible for calling into the Rex program. So this function is entirely implemented in assembly. And the first thing it does is that it will just save an old stack pointer before the program invocation. It will then call into the program. And if this program ever panics, then the Rex panic handler, which is implemented by us in the Rex kernel crate, will be invoked. The panic handler will clean up the resources and then jump to an in-kernel landing pad. The in-kernel landing pad will report this error to the kernel console and then jump back to the Rex exit label inside the in-kernel dispatcher function. Excuse me. So at this point, the dispatcher function will just restore the old stack pointer, which will effectively unwind the stack and make the execution as if it had returned from the program correctly. So the other important aspect of safe exception handling is that it must clean up the acquired resources. So the Tianyin ABI uses dwarf information to identify the resources they need to clean up. But our insight for Rex, or broadly in the context of safe kernel extension, is that it doesn't have to be so complicated, because those extensions can only acquire resources via helper functions. And therefore, only these resources will need to be released. So what Rex does is that it will just record the resources allocated via the helper function into a per CPU buffer. And then upon a panic, the Rex panic handler will just iterate the resources and perform the cleanups. So in terms of implementation, we implemented Rex on top of Linux 6.15. The Rex kernel crate contains the helper function interface and abstractions, the data type bindings, which are auto-generated by bindgen, and also program type specific code, which provides support to 5 existing BPF program types. So inside the kernel, we implemented the program loading and symbol resolution logic, as well as the Rex runtime. And we additionally add an LVM pass to the backend of Rust compiler to perform some Rex-specific implementations. So now let's move to the evaluation. So we evaluate Rex first on its usability, and apparently there's no verifier and there's no language verifier gap anymore. we used Rex to implement the BPF memcached cache, or BMC, from NSDI 2021, which this is a fairly complex BPF program that implements a kernel-level cache for memcached. And we found that Rex can actually allow us to write cleaner and simpler code. Our Rex implementation is around 300 lines of Rust code versus the original C code, which is around 500 lines. We also brought Rex to the OS classrooms at UIUC, where we designed 3 programming assignments on kernel networking and tracing. We found that our undergrad students can actually write correct Rex programs. So now, let me use the BMC cache invalidation logic as a case study of our usability improvement. So here, the snippet shows part of that cache invalidation logic, and specifically, this loop searches for a set command inside the payload. So there are several things to note here. The first thing is that the developers actually had to add an artificial limit, which is called BMC max packet length, on that loop to make sure that this loop fits within the verifier's complexity limit. And then, because the verifier always requires explicit bounce checks, you end up have a lot of boilerplate code that just checks the end of the packet. And third, you would just need to have this verbose logic to match that set command in the payload. And if we were to rewrite this thing into Rex, it will look like this. So the first thing you will notice that there's no longer that artificial limit to handle the complexity limit from the verifier. And the Rust slices already provides built-in bounce checks so that we no longer have to have those boilerplate code. And finally, the built-in methods of Rust slices also allow us to easily match that set command. So to conclude, the Rex BMC is just cleaner and simpler and easier to program. So we also evaluated the performance of Rex. So in this plot, we varied the number of CPU cores assigned to the network IRQs as well as the memcached server, and we measured the max throughput of 3 settings: the user-space memcached, the eBPF-based BMC, and the Rex-based BMC. So the takeaway is that Rex's usability and safety does not come at a cost of performance. And actually, Rex is able to achieve 5.4x speedup over user-space memcached on 8 CPUs. And Rex has exhibit a slight performance benefit over eBPF BMC, which is generally less than 5%, but it is there. So we attribute this to the simpler code as a result of better usability, as well as the better optimization job provided by the Rust compiler over the LLVM plus eBPF JIT combination. So to conclude, static verification in kernel extensions leads to poor usability and opens up to language verifier gap. And our insight on closing the gap is that we can actually leverage the language-based safety together with a runtime mechanism. And we realized our design in Rex, and we found that Rex can actually deliver usability without losing safety and performance. And our code repo is actually open sourced. You can find it on GitHub through this link. And thank you. I'm happy to take any questions.